Wait, let me see. Uno momento. Okay, all right. So what we're doing today, we're going to start infinite series. So this is 10.2. Infinite series. So the plan is we're going to do 10.2, infinite series. Then we are going to go back to improper integrals because it is very much related to what we're doing. And then we'll continue with 10.3. Okay? Okay. All right. Now, so what is a infinite series? So suppose you have a sequence. Let's say we have a sequence a sub n. Okay. So then, and let's say we take the partial sums of the sequence. So I'll underline this. So the partial sums are denoted S sub n. So the partial sums are basically the sum of the terms of the sequence starting from the first all the way to the nth. So here, for example, S sub 1 would equal to A1. S2 is equal to A1 plus A2. So then S3 would equal to A1 plus A2 plus. All right, very good. A1 plus A2 plus A3. Okay, now you can continue going in this manner all the way up to S sub n. So S sub n would equal to A1 plus A2 plus all the way up to A sub n minus 1 plus A sub n. So it's the sum of the terms of the sequence. And in these I wrote it starting at 1, but you could start a partial sum at a different number. Okay. So then, so those are the partial sums. So then we define the infinite series. The infinite series, which is written as the sum from n equals 1 to infinity of A sub n, as the sequence of partial sums S sub n. So the infinite series, it's not really a sum, it's more of a sequence of partial sums. So like you have the sequence would then look like capital S1 and capital S2, capital S3. So each, when you go from one term in this sequence to the next, you add one more term. Okay, so each one is a sum. So it's a kind of a sequence, but we call it a infinite series. So and so then we say that the infinite series converges to, let's say, L, and so then we write that the series n equals 1 to from 1 to infinity of A sub n is equal to L if the limit as n goes to infinity of the partial sums is equal to L. So in other words, the sequence of partial sums, if it converges to that number L, whatever it is, then you say that the series itself converges. Okay? So an infinite series is a kind of a sequence where every term is the sum of more and more terms. Yes? Okay, now, so let's do some examples. So examples of infinite series. So the first kind, so typically infinite series are more often than not, you can't actually find what the sum is, but so we're going to focus on finding out whether it converges or not. So one of the few that we are able to find the sum of are called the telescoping series. Okay, so here's an example of what a telescoping series looks like. It's the sum from 1 goes to infinity of 1 over n minus 1 over n plus 1. Okay, so all right, so let's start out writing out some of the partial sums just to get a handle on this. So what would s sub 1 look like? Well, it's just 1 over, it means plugging in n equals 1 into the sequence, right? So it's 1 over 1 minus 1 half, right? Okay. So what about s sub 2? The partial sum s sub 2 would be, add up the first two terms, right? So it would be 1 over 1 minus 1 half. So this is what I get when n is equal to 1, right? But then plus, then you plug in the next number, right? You plug in 2, and I get what? 1 half, yep, minus 1/3. This is what I get when I plug in n equals to 2, right? Does that make sense? Okay, so if I continue in this way, so I go up all the way up to the nth partial sum. So this is 1 over 1 minus 1 half, right? Plus 1 half minus 1/3 plus, and then I'm going to keep going, right, for a while. And then let me do this. Let's write down, what's the very last, what does the very last sum look like? The last 1 over capital N, right? Because I'm plugging in capital N, minus 1 over n plus 1. So that's the very last one. The one before that, what did that look like? 1 over n minus 1 plus, or sorry, not plus, minus, right? Minus 1 over n. Okay, now something really interesting happens here with the telescoping series. What do you notice? Yeah, so notice that the 1 half cancels with this 1 half, right? What about the 1/3? Yeah, this negative 1/3 is going to cancel with the one that comes after that, right? So then this 1 over n minus 1, that one's going to cancel with the one that comes before that, right? What happens with the 1 over n's? They also cancel. So actually, the partial sums are just equal to the number 1, right? This one right here. And then minus 1 over n plus 1, right? And what do you notice about the limit of that? So the limit as n goes to infinity of s sub n, the partial sums, right, is equal to the limit as n goes to infinity of, I just simplified it to this, right? 1 minus 1 over n plus 1. What is that equal to?
1.
That's equal to 1. So this series is, we say that it converges to 1. So that's equal to 1. So this is, because, so notice that all of the terms in the middle always are going to cancel out no matter how far you go, right? So as n goes to infinity, then that extra 1 over n plus 1 term goes to 0, and so you're just left with the number 1. Good times? Yeah, okay, all right. So any questions with that one? No? You guys want another one for fun? All right. Fun times number 2. How about the infinite series n equals 1 to infinity of natural log of n over n plus 1. All right, so what do you guys think about that? Does that look like a telescoping series? So what's the characteristic of the telescoping series? What's interesting about them? Well, yeah, you have 2 terms, but you always have a positive and a negative, right? And you're going to get cancellations between them. So does this look like it's going to be telescoping? It doesn't look like it, right? Is there a way I can rewrite it so that I can make it? You can, right? Because what is this equal to? Using the laws of logarithms. ln of what? N minus ln of n plus 1, right? So notice that you have consecutive terms, and one's positive and one's negative, right? So then if you write out the partial sum, the nth partial sum, you're going to get, what does the first one look like? ln of 1 minus ln of 2 plus, well, let's write out one more. So the next one, when n is equal to 2, it's going to be ln of 2 minus ln of 3 plus dot 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 plus, what's the very last one look like? ln of n, capital N, right? Minus ln of capital N plus 1, right? So which ones cancel out? The minus ln of 2 plus ln of 2, right? Negative ln of 3 with the ln of 3. Ln of n cancels out with the 1 before, and so then what I get is that s sub n is equal to, what is ln of 1? Yeah, ln of 1, that's actually equal to 0. So the only thing left over is negative natural log of capital N plus 1. So, that's interesting. So then if I take the limit as n goes to infinity of the nth partial sum, this is the limit as n goes to infinity of negative ln of capital N plus 1. And that is equal to, as n goes to infinity? Yeah, it's infinity, right? Well, negative infinity, right? Because of the negative on the outside. Okay, so does it converge? Does the series converge? No. What do you say when a sequence does not converge? It diverges. So the series diverges. Yes?
So is this like technique used to find limits?
Well, no, it's to find the, you're looking for the limit of where is it? Okay, so of infinite series. So the infinite series, remember, they're a special kind of sequence. They're a sequence of partial sums. And so when you find the limit of the partial sums, you're finding what that sum converges to. So it's kind of like an infinite sum, like the ones you did in Calc 1, but not exactly, because it's a sequence. Yeah? Okay. So any other questions? Questions? So our main focus of the chapter, a lot of it is dealing with the convergence of infinite series. So over the next week or so, we'll go over a bunch of different convergence tests. And it's similar to an integration in the way that you have to look at a series and you have to decide based on what it looks like, what technique to use, and that kind of stuff. So it's interesting stuff. Okay, so let's see. Let's go up here and let's do. All right, so let's take a look at another kind of series. So this is called the geometric series. So geometric series is the other kind of series that we can actually find the sum of. So let's see. So the geometric series looks like this. You have the sum n equals to 0 to infinity of c times r to the n. Okay, so here c is some constant, yep. And then r, bless you, r, this is called the ratio. Okay, so what we're going to do is, so this series doesn't always converge. It might look familiar. How many of you guys have seen this series before in some other class? Yeah. Okay, what class was it? Did you, or you just kind of, it looks familiar? B Calc. Okay. Just curious, you know. Like Curious George. Curious. Anyways, yes.
What characterizes the telescopic series again?
That it has this property that the terms in the middle of the partial sums every single time, they always cancel out in one way or another. Yeah. Okay. Boop, boom, ba-dum, ba. All right. So geometric series. So the question is, does it converge? When does it converge? What does it converge to? And so any ideas? What do you notice? Just by looking at it, what does your gut tell you? Does your gut tell you anything?
What's the ratio?
Well, it's a number. That's what it's called. It's called the ratio, but it represents a number. So our task is to find out, does it always converge? Does it always diverge? Or is it certain values of C and R that make it converge or diverge? So can you guys see one number that it definitely diverges? Or converges, whichever one. Like think of simple numbers and you go, oh, it definitely converges if blah. If what's 1? Well, n is going from 0 all the way to infinity, right? But if r is equal to 1, then what does that look like? So this is just us like brainstorming, you know, because brainstorming is really fun, you know, brainstorming. So it's like we're over here.
Do you have your breakfast this morning?
I don't know. Why?
It's the first time you've drawn a picture of one time.
Oh.
Remember we had our scuba guy and then he came and guacamole.
The scuba guy with the guacamole. Well, I don't know. Yeah.
So you remember something in class. I learned something.
That's good. At least you learned something. The scuba diver? There was a triangle. It was easier than the scuba diver. Anyways, okay, back to the problem. So this is what we're thinking. If r is equal to 1, what does this look like, the sum? What does the first term look like? C plus the next term? C plus? And goes on forever, right? Does that converge? So C is a number. So it's like adding 2 plus 2 plus 2 plus 2. How many times? Infinitely many times. Does that converge? Okay, so it definitely diverges, right, for that. Okay, what R value does it definitely converge to? Like, oh, it's obvious. 0, right? Because if R is equal to 0, then what do you have? Yeah, the whole thing is just 0, so you don't need it. Okay, so diverges R of 1, converges R 0, and then we have a whole bunch of other numbers that we have to think about. So, okay, at least we have an idea, you know, a hunch. So we're over here. This is us brainstorming. Okay, so anyways, so how many techniques do we have to test for convergence? We have 1. What's the only thing we know how to do?
The MCT or MTC.
No. So if you rewind to the beginning of the day today, let's see, 30 minutes. All we know how to do is to write it out, right? And see if we can find something, right? Write it out. Okay, so we write out the partial sum. So we go, okay, let's see. If I write out the nth partial sum, so what does the first term look like? C, okay, plus. Second term.
Why would it be 0?
Well, it starts at 0. The geometric series always starts at n equals 0. Yeah. Okay, what's the next term? CR. Okay, the next one. CR squared. The next one. CR cubed. And then at the very, very end, I have CR to the n, right? CR to the n minus 1. Okay. Now, does that look easy to manage? If we're looking at n going to infinity, this is quite a challenge, right? So the telescoping was great because everything in the middle canceled out, and all we had to do was look at the first and the last, and then we had great times with that, right? Okay, so then what we're going to do is we go, well, that looks like quite a big challenge. So we go, well, let's see if we can get rid of all of those middle terms somehow. And so we are going to do a neat little trick. What I'm going to do is, let me move this over a little bit. We are going to multiply S sub n times r. And then what we're going to do is we're going to subtract the two. And what do you think is going to happen?
Subtract what, I'm sorry?
Subtract the two. S sub n and r times S sub n. Because they're kind of similar, right? Similar. Here, let's start writing it out so that you guys can see. So r times S sub n basically takes all of these and it multiplies it times r. So what's the first term going to look like? CR. Okay, so let me line them up. I'll put it right here. CR plus. Second term is CR squared plus. Now, the very last term is going to be a C. If I multiply the last one in S sub n by r, it's going to be CR to the n plus 1, right? Does that make sense? So you're still going to have the CRn and CR to the n minus 1. CR cubed, I guess we can write it. So basically we grab, let me see. Okay, so all we did is we had the S sub n and we multiplied the whole thing by r. So that means that every single one of these is going to change from whatever it was to 1 degree higher in r, right? Does that make sense? So this C turned into CR, the CR turned into CR squared, and so on and so forth until CR to the n turned into CR to the n plus 1. Thumbs up?
It's just that space you left. It kind of looks like
What space?
where the C is. It's because that's the term that's multiplied by r, so we just move it over.
Oh, yeah. That's why I moved it over. Because remember what we said is we are going to then subtract the two. So check this out. We subtract them. Bam. What do I get when I subtract them?
Then build CR.
Bam, 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 bam. So what do I get on the right side? What am I left with? Look at all that. Yeah. Awesome. C plus CR to the n plus 1. Sweet. Wait, minus? No, plus, no? Oh, yeah, you're right. Oh. Just making sure you guys are paying attention. Yeah, minus, right? Because we subtracted this one? Yes.
You can just subtract them,
Well, it's kind of like you can just, if you have 2 and you have 3, well, you can just subtract 2 minus 3, you know? It's just like you're just playing around, you know? You're having a ball.
But like that's
Like,
not even the same thing anymore.
well,
Like, when
right.
you subtract 2 and 3, it's not the same.
Exactly. You're exactly right. So now I don't have Sn and I don't have Rsn. I now have Sn minus Rsn. So this is something different, right? Okay. Yes, exactly. There is more. Because now, so what I want is I want a simple expression for Sn. So then I go, hey, mister, if I want to get just Sn by itself on the left side, what do I do? Yes, I factor. What do I factor out? Well, yeah, I factor out Sn, yes. And then what am I left? Oh, hey, don't jump. Okay, 1 minus r. And then on the right side, I'm left with c minus cr to the n plus 1, right? So then what is Sn equal to? So S sub n is equal to this divided by 1 minus r. And let me factor out the c so that I don't have to worry about it. So c times 1 minus r to the n plus 1. Okay, now let me ask you this. Which one do you prefer? This one that we had up here in blue, do you prefer to work with that, or do you prefer to work with this? Option 1 or option 2? 2, right? It's way simpler. Okay, so then we go, So now we go back. So my picture of the brainstormer is now off the picture, so I need to come back. Wait. Brainstorming, number 2. He comes over.
I didn't know you could travel across an S sub n though. You sure just have to like travel around or use a rowboat or something?
He ate too many carrots. Or something. I don't know. You know, if you eat too many carrots, you get orange. Yeah. Have you guys tried it before? I tried it when I was a kid. You do turn orange. It's
I was told it makes your eyes burn.
the what? All right. Anyways, okay. So brainstorming session number 2. So this is what I'm wondering. For what values of r does S sub n converge or diverge? And I ran out of space in my little bubble, but that's okay. All right. So this is the question that I'm asking myself. So then you look at it and you go, what do you notice? What is the, as far as convergence, meaning what values of r make this blow up as n goes to infinity or go approach some number as n goes to infinity?
0.
Well, yeah, we already know 0. That one's too easy. Well, we already know the divergence for 1 and it converges for 0. So those are out of the map. So let's say, okay, so let me ask you this. All right, so since we're brainstorming, right? We love brainstorming. Let's say, for example, r is equal to 2. What would happen as n goes to infinity? What happens to S sub n? Or let me rephrase. So out of all of the stuff that you have going on here in Sn, what's the term that will cause the most trouble? R to the n plus 1, right? Because c is a constant, r is a constant. So this is really the one that you have to take a look at, right? This is the one that can give you either a lot of trouble or no trouble at all, right? Okay, so imagine r is 2. As n goes to infinity, what happens to that term right here? It goes to, so 2 to the n plus 1 goes to infinity. So S sub n what? Diverges, right? What's another value of r that it diverges for, that it also blows up? 3. If r equals to 3, the same thing. What else? 5, 6, 7, 8, right? Okay, so there's a lot of numbers that term blows up, right? So what terms does it not blow up for? Shrinks. For what? -1. Not quite. In between, yeah, if it's a fraction that's less than 1, right, then what's going to happen to that term? So like, for example, if you take a look at 1/2 to the n plus 1, what happens to that as n goes to infinity? That goes to 0. So the only thing left over would be this would go towards 0. So you would just have c over 1 minus r, right? So, okay, so let's summarize this.
I thought you said R was just a constant, like a number.
It is, but it's set at the beginning at some constant. So if that constant is less than 1, then it's going to converge, right? If that constant is greater than 1, it is going to diverge, right? From right here, if you look at this expression right here, this is giving you the problems right there. Problems. Okay, so let's write this down. Let's summarize what we just learned out of our brainstorming session. So the geometric series n equals to 0 to infinity of c times r to the n is equal to if r is between -1 and 1, so in other words, if the absolute value of r is less than 1, then this is going to converge to c over 1 minus r. Where did that come from? It came from right here, right? If this goes, if r is between -1 and 1, then this term right here is going to go to 0, right? So the only thing left over is going to be c over 1 minus r. Yes? Okay. So then if r is greater than or equal to 1, then this series will diverge. Yes?
I thought n was your variable.
N was our variable.
The variable.
Well, yeah, and it goes from 0 to infinity. You need an example. Well, everybody needs an example. Yeah, that's what's coming next. Okay, so example time. All right, so what is it? All right, so let's take a look at the number 9.999999999999999 that goes on forever. So this number, you can rewrite it as 9 plus, this right here is 9, what do you call this? That's 9, no, this place, that's 9 tenths, yes, 9 tenths plus 9 100ths, right, plus 9 1,000ths, right, and then plus, so this keeps going on forever and ever now, right? So we can rewrite this as a, this is a geometric series. This is the series defined by n equals 0 to infinity of, what would this look like if I were to rewrite this as a series? So I would have a 1 over 10, right, to the n, and then I'm missing one more thing. 9 times 1/10 to the n. So this is a geometric series, right? In this case, so this 9, that's c, right? And then my ratio r, that's 1/10. Does that make sense? Yeah? You guys with me? So this is 9 plus 9 tenths plus 9 hundredths plus 9 thousandths and so on and so forth, right? Yes! That is exactly right. Okay, so okay, so what do you notice about r? Since r, which is equal to 1/10, is less than 1, right? Then the series converges to so let's write this out again. So I have, oh wait, I don't want to leave my, okay, so I have the sum n equals 0 to infinity of 9 times 1/10 to the n is equal to, so going back to what I found, right? So this is equal to c, which is 9 over 1 minus 1/10, which is equal to 9 over 9/10, which is equal to 10. So 9.9999999999999 forever and ever and ever is actually equal to 10. Ta-da! Applause? Yeah? Okay. No, not in the mood for applause. Okay. Questions? Geometric series? No? No questions, huh?
What's a
Yes, Thomas?
So for all sums that have the form c times r to the n, we can use the same like little bracket thing that we said that it's for r is greater less than 1 and c is over MSR diverges for r is greater than.
Yes, but notice, notice that the geometric series, it's, what does n start at? 0. Would it be the same if I start at, say, 5? The sum wouldn't be the same, right? Because you're adding a bunch of terms, right? If you take out the first 5, then that's not going to be the same number, right? Okay, so let's do that because that's an extension of what we were just talking about. So let's say, for example, I have a geometric series. So this idea is very important because you're going to use this a lot. This is changing the index of sums. So you might already know how to do this, but it's good to review. So this is, let's say I start at some number m, and we'll do the same geometric series, although the idea is the same no matter what the series is. So here, instead of starting at 0, I'm starting at m. So the question is, well, can I use the same formula that I used if I started at 0? And you say no, right? It makes sense that it's not the same because you're taking out the terms from the beginning. So if you don't add those up, well, it makes sense that it would add up to a different number, right? Okay, so then what you do is you go, okay, so I want to be able to use the formula. You want to change this sum so that it starts at 0. So then the question is, how does that change the n's that are already there? So, like for example, so on your sheet, don't erase this, although I'm going to erase and then I'll write it down again. Let's say, for example, this is for now. Let's just say this is starts at 5, right? So what is the first term here of this sum? CR to the 5th, right? Plus CR to the 6th, and so on and so forth, right? Okay, so if you want it to start at 0, what does this exponent have to be for them to be equal? This has to be so you want it to match, right? So you want the first term to be CR5, so this would have to be n plus 5, right? Does that make sense? So notice here when n is equal to 0, this is r to the 0 plus 5, so this is CR5. When n is equal to 1, this is CR to the 1 plus 5, or 6. So they match, right? So basically what you did is you took 5 away from here, right, to get to 0, and then you added 5 over here to have it match. Does that make sense? Yeah? Okay, so let's go back to n now. Technical difficulties. Hold on. Sorry. Okay. Oh my gosh. All right. Okay. There we go. All right, so now we have, so if this is m, and I want to change it so that it starts at 0, then this is going to be CR to the n plus m, right? Okay. Now the question is, specifically in this case of the geometric series, how does that affect the formula? So, oh, I forgot to put infinity here, but okay. So let's rewrite it. How could I rewrite this the r to the n plus m? Using the laws of exponents, this is equal to r to the m times r to the n, right? Yes? Just using the laws of exponents? You guys agree? Okay, now m is a constant, right? So then this CR to the m, this is a constant. And isn't this now in the form of the geometric series? So then what is this? If r is less than 1, then what does this converge to? This is going to equal to, instead of c over 1 minus r, this is going to be c times r to the m over 1 minus r. Does that make sense? Because you have a new constant from changing the index, you've created a new constant r to the m that you have to then include in your sum. Does that make sense? You guys with me or yeah? Okay. Okay. So let's do a quick example related to the one we just did. Let's say I have 0.999999999. And if I'm going to write this as a series, this is, it's the same series, right? Except that what's the difference? I start at n equals to 1, right? Because the first one is 0.9 or 9/10, right? So it's the same series, it's just you start at 1 over. So we already know r is less than 1, and so it's going to converge, but instead of converging to 10, this time it's going to converge to c times r to the m. What would that be? So c is equal to 9 times r to the m, which is 1/10, right? This is r to the m, which is 1, right? That's how many my index is shifted over. And then over 1 minus r, which is 1 minus 1/10. So then what I get is this is equal to 9/10 over 9/10 over 9/10, which is equal to exactly the number 1. Ta-da! So what did we learn today? That 0.9999999 is equal to 1. Yeah. Well, plus you learned a lot of other things. Brainstorming and series.
Group work.
Group work. Yeah. Teamwork.